Right, let's get some physics done. It's an Edexcel Combined Science Paper 5, which means it's a Physics Paper 1. It's the foundation tier, and it's from May 2018. 1 hour and 10 minutes, worth 60 marks. Question 1. Which of these speeds would be normal for a person walking? Well, you take about 1 metre as a step per second. So that's 1 metre per second. Part B. Figure 1 shows a block hanging from a spring balance, and it's showing 3.8 newtons. Use a word from the box to complete the sentence below. The quantity measured by the spring balance in figure 1 is, well, if it's in newtons, that's weight. Out of those options to choose from, weight or force. Question C. A toy car has a mass of 0.1 kilograms. The toy car accelerates at 2 meters per second squared. Calculate the force producing this acceleration and state the unit. Use the equation force equals mass times by acceleration. Right, there's your mass, there's your acceleration. Multiply them together, out comes the answer, 0.2 newtons. Part D. Use words from the box to complete the sentences below. Vectors have size and direction, and scalars have only size. If they ask you for some examples of vectors, you could say a force or displacement. An example of a scalar could be speed or mass. Question 2. A sound wave in air travels a distance of 220 meters in a time of 0.7 seconds. State the equation linking speed, distance and time. So speed is distance divided by time. Part 2. Calculate the speed of the sound wave in air. So that was the distance, that was the time. Do that divided by that and it pops out as 314.29. I've done it to 2 decimal places because that time was to 2 decimal places. Part B. Figure 2 shows water waves spreading out from a source. A student measures the wavelength of the waves. He uses a ruler to measure the distance from one crest to the next crest. So there's the crests there, each one of these large ripples. Explain how to improve the student's method for measuring the wavelength. Right, instead of just measuring from crest to crest, one wave, why don't you measure multiple crests or multiple wavelengths and then divide by the number of wavelengths? So if I measured from there across to there, then that's 2 wavelengths, so I'll just divide that distance by 2. Or if I measured from there, 1, 2, that's 3 wavelengths, so whatever that distance is divided by 3 to get the wavelength. Question C. Sound waves are longitudinal waves. Water waves are transverse waves. Describe the difference between longitudinal waves and transverse waves. Standard stuff. Longitudinal waves, you say that the vibrations are parallel to the direction of travel. So if the wave was travelling that way, the vibrations are parallel, which means in the same direction. And transverse waves, the vibrations are perpendicular or at 90 degrees to the direction of travel. So again, if the wave was travelling this way, the vibrations are going up and down at 90 degrees. Question 3. Figure 3 shows a spinning flywheel. State how energy is stored in a spinning flywheel. Well, it'll be kinetic energy in the spinning flywheel because it's moving. Part 2. State one way to increase the amount of energy stored in the flywheel. Okay, so the equation for kinetic energy is a half mv squared, so you could increase the mass or increase the velocity, and that would increase the kinetic energy. Part B. Figure 4 shows a skier going down a hill. She descends through a vertical height of 200 meters. Get in the habit of writing what you know when you know it. So we know that's the height h. The skier's mass is 65 kilograms, so that's m. Calculate the change in gravitational potential energy. Use this equation. So the change in the gravitational potential energy equals mass times by gravity times by the change in height. So the mass was 65 kilograms. Gravitational field strength on the Earth is 10 newtons per kilogram. Usually they'll give you it, but if not, make sure you learn that. And multiply it by the height, which was 200 in this case. And your answer comes out as 130,000 joules. Part 2. At the bottom of the slope, her speed was 36 meters per second. Calculate her kinetic energy at the bottom of the slope. So they've gave you the equation for kinetic energy, which they always will at this level. So a half times by the mass, it's the same person, so the mass is still 65 kilograms, and multiply that by 36 squared. Remember to do the 36 squared first, then multiply it by 65, and then multiply it by a half. And that should come out as 42,120 joules. Part C. Describe how her speed at the bottom of the slope could be determined. Alright, well, speed, you need to know the distance and the time. So you'll get a mark for putting that. Measure the distance using two markers. So a marker at the start and a marker at the end, down at the bottom of the hill. And measure the time to travel between the two markers. And you can see it to start the stopwatch at marker 1 and then stop the stopwatch at marker 2. If it was worth anything more than 3, I would say make sure you measure the distance with a trundle wheel and measure the time with a stopwatch. Question 4. Part A. State 2 non-renewable energy sources. Right, well here's all 4. Coal, oil, gas and nuclear. Part B. Figure 5 shows the renewable energy sources used in the UK in 2015. State the energy source that gave the greatest amount of renewable energy for the UK in 2015. Well, they're all renewable energy. So that basically means that the biggest part of the pie is what we're looking for, and that's bioenergy. Part 2, justify your choice. Well, it's the largest part, isn't it? Bioenergy, it's the largest fraction of the pie chart. Just be careful in case they do a mixture of renewable and non-renewable. You'd have to make sure that the biggest part was actually the renewable one that they were asking for, not non-renewable. Part 3. State which of these energy sources gave about 20% of the energy from renewable sources in 2015. So 20% is a fifth of the pie. So you're looking for something that's about a fifth. That one looks about a fifth or about a quarter-ish. It's the closest to 20%, so the answer's wind. Part C. Figure 6 shows all the energy sources used in Canada in 2014 and a prediction for 2040. Discuss the effects of the environment of 2 predicted changes between 2014 and 2040. Now you've got to be a bit careful here because oil looks a little bit like biomass, so don't get them mixed up. Right, let's start with this dotty one. So this is the wind. So the wind goes from 7% and it's going to go up to 11%. So the wind use is going to increase. What effect will that have on the environment? Well, there'll be more visual pollution because those wind turbines are pretty big. Visual pollution just means something's going to get in the way when you are looking. You're not going to be able to see the nice countryside anymore because there's a great big wind turbine in the way. The second change, I've went for biomass, so we can see the biomass and the solar energy. So just coming over to here, that's going from 3% to 5%. So the biomass, solar, geothermal use is going to increase, and the effect it'll have on the environment is there'll be less CO2 released, so less global warming. So carbon dioxide, CO2, causes global warming. So if we're using more of that, we're going to get less of that released. And that'll do for the 4 marks, but I've just wrote everything else. So this one here is the uranium. So you can see from 10% to 6%. So they're going to use less uranium. So that means there'll be less radioactive waste. This one here, coal and coke. There's less coal and coke, so that means there's going to be less CO2, so less global warming. This one here, from 3% to 2%, so that is the oil. So there's less oil used, so again there's going to be less CO2 and less global warming. Coming down to this stripy one, that's natural gas, so that's going to increase as well. So more natural gas. Well, do you know that natural gas does not give off CO2? So once again, there'll be less CO2 and so less global warming. That's what these little dashes means the same as above. And if we look at this largest part, that's the hydro, wave and tidal, you're actually going to go from 55% to 51%. So there's going to be less hydro, wave and tidal. Now, that doesn't necessarily mean that they're going to use more coal, oil and gas, which would increase the CO2. We can't make that assumption. So I've just said, well, look, if we're using less hydro, wave and tidal, that means it's going to be easier for the ships to sail in the sea. That's what I've went for there. Part D. Figure 7 shows a wind turbine. Explain how unwanted energy transfers could be reduced in the gearbox. Well, just lubricate the gearbox, and that'll reduce the friction between the moving parts, which will reduce energy being wasted as heat. So you can see I've gave 3 answers there for 3 marks, even though it's only worth 2. So that's just to make sure I've covered it correctly. But that's always the same sort of answer whenever you've got something that's moving. How do you get rid of unwanted energy transfers? Use lubrication. It reduces friction. Question 5. A student investigates what happens when light travels from air to glass. Figure 8 shows some of the apparatus used in the investigation. So it's a standard refraction experiment. In figure 8, angle Y is the angle of. This here is the angle of refraction. So the answer is D. If they asked you what this angle was, that's the angle of incidence, because that is where the light is going in. Part 2. Figure 9 is a graph of the students' results. Use the graph to calculate a value for angle Y divided by angle X. So you just pick any value of angle Y and its corresponding angle X. So that is 10 degrees for Y, and that is 16 degrees for X. So 10 degrees divided by 16 degrees comes out as 0.625. Part 3. The student concludes that angle Y is directly proportional to angle X. Explain what the student must do to test this conclusion in more detail. Well, look, they haven't got enough results really, have they? So if they repeat the test, use more angles of X and Y. So remember, they're changing X on purpose to see what Y comes out as. So if we use larger values of X to see what Y is, that'll be great. We'll have a lot more data on our table. And if it is directly proportional, when X is doubled, Y should double, as well as going through 0, 0, which we can see it already does. Okay? That's great. And directly proportional, it would also mean if you were to make X 3 times bigger, Y should get 3 times bigger. Part B. The speed of light is that. The wavelength of yellow light is that. Calculate the frequency of yellow light and state the unit. Use the equation. So just put the speed in and divide it by the wavelength, and out pops your answer. And if it's frequency, it's measured in hertz. So the answer, I've just rounded it up to 5.2 times 10 to the 14, but I have put the longer answer there if it was required. C part 1. Give one colour of light that has a longer wavelength than yellow light. So that's either red or orange. So remember, Richard of York gave battle in vain. We're looking for, red, orange, yellow, green, blue, indigo, violet. Red's the longest colour. So red or orange is longer than the yellow. Part 2. Give one colour of light that has a higher frequency than yellow light. So if you've got a long wavelength, that means you've got a lower frequency. So we're looking for any colour of light that has got a shorter wavelength than yellow, because then it'll have a higher frequency than yellow. So once again, Richard of York gave battle in vain. So we could have had green, blue, indigo or violet have all got shorter wavelengths and higher frequencies. Remember, if the wavelength goes down, the frequency goes up. Question 6. Figure 10 shows a Geiger-Müller tube, it's a GM tube, used for measuring radioactivity. Describe how a teacher should use a Geiger-Müller tube to compare the count rates from two different radioactive rocks. I've got a nice video on this on my channel, so click the link above if you'd like to check that out. Right, so what we need to do is we need to pop a rock here at a certain distance, and we'll find out how much radiation's coming off the rock and going into the counter. Every time a piece of radiation goes into the counter, you'll hear a little click. First of all, however, find out the size of background radiation, so make sure you keep all the rocks out of the way while you do that. Then, place a rock, the first rock, a certain distance from the Geiger-Müller tube and record the count rate for that rock. Leave the rock in front of the Geiger-Müller tube for a certain amount of time. Then repeat the above steps for the second rock and make sure that you tell the examiner that you're going to keep the rocks there for the same length of time and at the same distance away from the Geiger-Müller tube. Now remember to subtract the background radiation away from the count rate of each rock to get the count rate of the rock, and repeat the readings for each rock and take averages. So we should easily get 4 marks for that, probably 6 marks if they use that for the 6 marker. Part B. A hospital uses a radioactive isotope with a half-life of 6 hours. A technician measures a count rate of 80 counts per minute from this isotope. Complete the graph on figure 11 as accurately as possible to show how the count rate from this isotope will change from the time of the first measurement. So what they're saying is the half-life is 6 hours. So that means that the count rate or the activity is going to half every 6 hours. So at a time of 0, it said that the count rate was 80. So 6 hours later, so go along to 6. Now we want half of 80, which is 40. So just go up to 40, put your cross there. Now, that means another 6 hours later, so 12 hours, it's going to half again from 40 down to 20. So go to 12 hours and go to 20 and put your cross there. Now, make sure that you know that every 2 squares is 1 hour. And finally, from 12, if we add another 6 hours on top of 12 hours, we'll get to 18 hours. So go along to 18 hours, and it's going to half again from 20 down to 10. So there we go. That's what your typical half-life graph's going to look like. It's what you call an exponential shape. So try to draw it as neatly as you can, as smoothly as you can. Part C. A radioactive rock is placed near to the front of a Geiger-Müller tube. A radioactivity count rate is first made in the air. The count rate is measured again with each of these 3 different absorbers between the rock and the GM tube. Figure 12 shows the count rates measured. A scientist has an idea that the rock emits 3 different types of radiation. So that's alpha, beta and gamma. I've got a nice video all to do with types of radiation. Click the link above. Explain how the data in this table supports the scientist's ideas. So, when there is 3 centimeters of air, the count rate is 1,272. So you've just got the rock 3 centimeters away from the Geiger counter, and that's your count rate. Now what they do is they put a thin sheet of paper in between the rock and the counter, and the count rate goes down to 931. Now we know that alpha is stopped by paper, and we also know that alpha must be present because the count rate decreases when the paper is used as the absorber. So beta goes straight through paper, and so does gamma. So alpha is obviously present in the rock because the count rate's decreased when you put the paper in the way. Now what they do is they then put some aluminium in the way. Now beta is stopped by aluminium. So beta must be present because the count rate decreased when 3 millimeters of aluminium is used as the absorber. So the fact that that count rate decreases goes down to that count rate when you put the aluminium in the way, that means that there must be some beta there. So we've already got rid of the alpha, now we've got rid of the beta, and we're left with 21. Now if you put 2 centimeters thick sheet of lead in the way, the fact that this is still 21 means one of 2 things. We know that gamma is the only type of radiation that can penetrate lead. So gamma is present as there is still a count rate when the lead is used as the absorber. Unless, of course, 21 is the actual background count rate, in which case there is no gamma present. So what you'd have to do is get rid of the rock completely and see if the background rate is 21. If the background rate was, say, 10, then we know that there must be a count rate of 11 coming from the gamma in this case. So that is a standard question, and they often use it as your 6 marker. So I hope you've understood the way I've explained it there. Again, check out my video, all to do with the types of radiation, alpha, beta and gamma, the penetration power, the ionization power, and what they're made of. And that's the end of the paper. So I hope that was useful for you. Make sure you've subscribed to the channel because I'm putting lots more videos on. Smash that like button and hit the bell so you get notified the next time I'm popping a video up. Work hard and be nice. Good luck with your mocks and your exams in the summer. Bye for now.